The floor is yours.
Thank you. Good afternoon, you all. And I'm glad that you are here since it's almost the last presentation and soon the conference will end. I'm going to present a research which is devoted for the fatigue life estimation of the CFRP composites under multi-axial loading conditions. My name is Szymon Duda, and it is a collaborative work between my university, which is Wrocław University of Science and Technology, and University of Memphis in the States. So at the beginning, let's name the challenges. And I'm sure that we all are familiar and aware of multi-axial fatigue and the challenges that came with. So if we consider composite materials, the problem is more comprehensive due to the failure mechanisms that appears sometimes simultaneously, and they are devoted into some stages, not like in metallic materials. Moreover, if we think about metallic materials, the multi-axial fatigue, it's quite well described in contrast to the composites. So besides this, if we consider fiber reinforced polymers, so even under uniaxial load, we can deal with the multi-axial stress states. In that, there is still need for the fatigue life estimation formula for estimating the durability and fatigue performance of the elements. Moreover, the application, the market of composite material is increasing every year, and we can see on the right side some of the applications which are used the composite materials. So moving on, I would like to again highlight the research objective, which is the approach for the predicting the fatigue life for continuous fiber composite materials under multi-axial fatigue load, and which takes into account the phase shifts as well as mean stress effect. And you can see the core of our research. So first step is devoted for the material characterization under monotonic load, then multi-axial fatigue experiments, fatigue behavior modeling, and then fatigue life prediction. The fatigue life or fatigue behavior modeling was based on my own experimental research on CFRP, and then I took the data from the literature to see how it works in terms of similar material from the same group, but with different stiffness. All right, so first, the static mechanical behavior. In this case, besides the flat coupons, which was used to deliver the elastic properties, I investigate the mechanical performance of thin-walled tubes, which were manufactured using a filament winding method under different quasi-static loading conditions. You can see the geometry of my specimen. So the external diameter was around 22 millimeters. And if we consider fiber composites, we can see that there are two coordinate systems. The first one is a global one, which is the laminate coordinate system. And in this case, the X is the direction of the axial force and Y is the perpendicular. But if we consider composites, we rather use the material coordinate system for one lamina, and it's denoted 1, 2, 3, where 1 is the first direction along the fibers and second is perpendicular. You can see on the right side the results from the static investigation. All right. Okay. So the material. Now it's correct. Okay, so simultaneously with the static experimental campaign, I developed or created a numerical model which was used for this stress and strain analysis. And you can see that if we consider such structure manufactured by filament winding method, we have a very specific pattern which is generated due to the technology, and it's called zigzag area, where the fiber where is the fiber ondulation, and there is a cross section of this part. So this is the red box here. You can see the comparison of the numerical results with experiments. You can also find the data on it in our paper in thin-walled structures. So there is this A region. So the problem is actually with the compression, because this model does not include the defects. In that, the numerical model overestimates the experimental the experimental results in this case. Okay, maybe 2 words more about it. So the model includes the nonlinear shear material model with progressive damage. Okay, so the model verification. So along with the experiments, we use the strain gauges as well as DIC system. And you can see here on the left side, we have the strain fields from the finite element method compared with the DIC. We see concentration, a local concentration along this fiber interweaving area. All right, so now after the static experiments, we move to the fatigue experiments. And again, like similar like in previous presentation, the test was done on MTS system 809, axial torsional one. So we also used the biaxial extensometer. Actually, here it's not shown, but besides this, the experiment was also enriched with the acoustic emission sensor. However, this is not, I will not present the results during today's talk. All right, so the axial force was applied as well as torsional moment. You can see the flowchart of the investigated parameter. So we have the biaxiality ratio. In this case, the biaxiality ratio is for the geometrical stresses, and it's equal 1. So the normal stress, the geometrical normal stress is equal to the shear stress for different load ratios, as well for various phase shifts, 0, 45, and 90 degrees. And so you can see the results, and in some cases, well, in this form, we cannot really say what is the impact of the phase shifts. Why? Because due to the low correlation in some cases, the effect is hidden. That's why if we think only about the positive R ratio, where there is no compression, which might cause additional challenges such as local buckling of the fibers. So we can see the effect of 90 degrees out of phase loading. And in general, the fatigue life results in lower life. Moreover, this is important point that those SM curves, they are plotted for the geometrical stresses, sigma, x amplitude. We see in both cases the same effect for R equal 0.05 and for R equal 0.5. If we think about the mean stress impact, since different load ratios were investigated, the situation is similar, especially for 45 degree out of phase load, as well as for R minus 1. That's why I excluded the data at this stage for analysis, since the effects were not properly visible. And so same like before, if we consider the positive load ratios, in phase load, out of phase, we see that the fatigue life differs if we include the mean stress. So for higher mean stress, the life is lower in both cases. So for in-phase and out-of-phase loading. So we have the fatigue experiments, the SN curves. Now we did macroscopic post-failure analysis, and this in all specimens that we tested, the crucial area was this interweaving areas where the where the damage or was observed. Of course, it was the damage, the final failure of this composite. We see that there was fiber breakage, which is quite obvious. But besides this, we observe the delamination between the layers. I would like to add that this specimen, the fiber orientation is plus minus 30 degrees. And now stiffness variation. So those stiffness variation has been presented for the displacement amplitude, and we see the gradual change in displacement. The fatigue test was force controlled, and in the last stage we see some progressive change in displacement, which we associated with the macroscopic damage development. It can be also seen here. This is from the biaxial extensometer, and we see gradual and linear decrease in normalized stiffness. All right, so now actually the most important part is the modeling, right, of the damage. So we decided to choose the concept known as a critical plane approach. There are some reasons for that, and the first one is it accounts the physics, and also it is quite simple because it requires only a proper stress analysis. Moreover, there are some recent papers which shows the applicability of this approach in terms of the short fibers composites. So that's why that was let's say, the current direction which we wanted to see and investigate it. So the damage parameter formulation. So based on the literature review and the experimental observation that we did, we assume that the debonding is crucial in terms of the investigated structure. In that, the driving force which causes the debonding, it's governed by the shear stress 1, 2, and this is another component which has also impact on this damage process, and it's the sigma to maximum. So this damage parameter has been used to calculate at a critical point the damage, and the plane of damage initiation was assumed as the maximum value of this. In this case, since we take into account the stresses along the first and the second direction, there are only two directions, since I have just two layers, plus minus 30 degrees. All right, so moving on. Stress analysis based on the developed numerical model, which includes this fiber interweavings area. This is important because there is a significant stress concentration. And for the critical point, which is associated with the stress extrema point, we calculated the damage. And you can find the more detailed description of the results in our paper, which is published in Archives of Civil and Mechanical Engineering this year. So the damage correlation, so the calculation are presented here, or the results which are connected with the damage parameter have been shown here. So we see the R is equal 0.84, the 90% prediction intervals, And based on this, here the damage was calculated not on based on the stresses that was plotted on the SN curves, so the geometrical. They were calculated based on the finite element model for the mesoscale stresses, sigma 2 and tau 1, 2. So the fatigue life prediction, based on this, we decided to propose a quite simple method. We calculate the damage for the 1 million cycles and associate it with the uniaxial load, which can generate the same damage value. And then correlating this with the UTS value. However, this value needs to be for the tubular specimen, not for the flat. We deliver this curve, this dot 1, and the algorithm has been presented here. Another thing, so applicability for other material, it's a pretty similar material since the damage mechanism should be the same. However, the stiffness of glass fiber reinforced polymer is lower than in terms of the carbon fiber. So I took from the literature different data. For layup configuration, you can have a look here, different biaxiality load ratio, and that's the correlation for our damage parameter. So let's move to the conclusions. So based on the obtained experimental data, the phase shifting has negative impact, as well as the mean stress, which results in shorter fatigue life. And the stress-based damage parameter with good agreement describes the mean stress and phase shifts effect in fatigue life estimation. I would like to also present you the data that I'm currently working on. So I'm trying to implement or see the applicability if there are additional parameters which affects the fatigue. So the biaxiality, lower biaxiality 0.5, it means the normal stress, the geometrical is twice the shear. We see the shifting in SN curves. The same for the out of phase loading, and also the notch effect on fatigue life. All right, so thank you for your attention.